Hi, I'm Neil Elliott. I'm going to be your host for the Industrial Breakout session today. I'm going to also be your moderator for the session. And as you come up with questions, if you'll put them in the chat, and I will be following those along and then posing them after we hear our presenters. Also wanted to let you know that the presentations from all three of our presenters will be on the symposium landing page, as will information on their bios. Now I'd like to go ahead and get started. So we're going to start out this session with a global perspective and then take a look at what's happening in one of the globally leading countries in the industrial policy space, Japan. And then we'll conclude with a technology focus, really looking at how do we enable electrification in the industrial sector, looking at industrial heat pumps. So I said we'll start with the global perspective from an old friend and collaborator of ACEEE, Chris Bataille. Chris has been involved in energy and policy for more than 20 years as a researcher, economist, and executive. He is currently an associate researcher at the Institute for Sustainable Development and International Relations, I think better known to all of us as IDRI, and has been also working as an adjunct professor at Simon Fraser University in Vancouver, BC, and as a consultant. He's just completed a 5.5-year project as lead editor of the special issue on climate policy on deep decarbonization pathways, and is leading an effort on deep decarbonization pathways for heavy industry. And he has just returned from the IPCC meetings. And so I think that'll be a great way for him to start off, is tell us a little bit about what's happening on the industrial front on the globally. So with that, Chris.
Great. Could we advance? Thank you very much for that kind introduction, Neil. Okay, I thought I emerged over the weekend. You may have heard we did basically a 36-hour round-the-clock negotiation session to get Working Group 3 approved. The report came out Monday. I was one of the lead authors for industry, involved in the technical summary and the summary for policymakers. But I thought I would pull something out of the 120 pages in the industry chapter that may be most use and interest to this crew. This is a figure that I've been working on for several years, and just click once, please. And we bust our heads on, really, we bust on our heads on it for a long time, and I'm still not satisfied with it. And I'd love to hear some discussion. So what we did is we looked at all the, our mandate was how do we get industry to net zero emissions by 2050? So in roughly a generation and a half, how do we go from the largest, the fastest growing source of emissions in the global economy to net zero? And through our literature review of literally thousands of papers, we came up with these big strategies. So there's the demand for industrial products. There's how much the fundamental demand for housing, the service product intensity. So how many meters squared of steel, cement do we need for a given building? How effectively do we use concrete or steel for a meter squared of a building? And then how do we reuse the various components? Then we get to energy efficiency, which is the core interest of this crowd. And we go on to fuel switching within that, CCU and CCS. Now, if we can go to the next slide, please. I'm just going to ask you to click forward about 6 times, please. Sorry, I was anticipating just until we get the big red box at the bottom. Okay, stop there, please. Yeah, so marching through, for all the industrial sectors, we march through these big interacting strategies. We looked at design to make better use of steel, cement, other materials for infrastructure, building and vehicles. However, that requires a supply chain overhaul of architectural, civil engineering, construction firms. Looks like about 26 to 40% reductions can come out of that. In terms of circularity, we can recycle concrete by grinding up, recovering unreacted cement and aggregates. The big area for recycling is going to be steel, where we can get the maximum amount of iron product back out of the economy, but it needs less contamination. We have to do it at a higher quality level. And maybe in 100, 150 years, we won't need new primary iron. There'll be enough steel circulating in the economy that it'll only need small top-ups. Where energy efficiency really kicks in this system is in the production decarbonization, and I would argue in a different way than we've been thinking about it up until this assessment. So for steel, up until 5 years ago, we thought it was all going to be about efficiency and CCS, but it turns out that there are new primary processes that have been largely developed but just not used because they're more expensive to completely eliminate emissions in steel using direct electrification and hydrogen made either through electricity or from methane and CCS. Now, those processes are just coming off, they're just at the near commercial stage. They need decades of evolution to get them to the point where they're at their nth level of energy efficiencies. So we're leaving the zone where we've been working for almost 100 years, perfecting the blast furnace, basic oxygen furnace. We're going to make a jump to a whole new set of processes that need a whole new set of evolution of energy efficiency evolution. For cement, cementitious material substitution is our key near-term strategy, making better concrete mixing, alternative fuels, again, and then CCS for process or for heat. And then finally, for chemicals, there are over 40,000 chemicals in use. Most of them come from 7 key feedstocks. And the key to decarbonizing those is going to be clean hydrogen, low GHG carbon from several sources, and cleaning up it's the oxygen, hydrogen, and the carbon, and also the heat and electricity to process all of these. Now, what I would argue here is that we're about to embark on a whole new several decade long process of improving the energy efficiency of all of these new processes that allow us to get to net zero. Can we go to the next slide, please? And just click down until, and one more. Oh, too far. Stop there. It's good. Okay. Now, because we're going to a whole new set of processes in order to produce the large materials that we need, there are likely going to be structural energy efficiency policies from restructuring supply chains. So for example, we currently make primary iron and steel near coal and iron ore and move it where it's needed. If we're using hydrogen direct reduced iron, we can make it near the iron from cheap, clean electricity, which is the green hydrogen, or cheap methane and CCS, which is blue, and then move the green iron to the electric arc furnaces where it's needed. Electric arc furnaces, on the other end, can stay where they are, near markets and supply chains, and there's a lot of room for improvement in electric arc furnaces going forward, especially in changing the anodes so that they don't emit CO2 as they're operated. Existing BF blast furnaces can be preloaded with up to 30% green iron, co-fired with hydrogen until the end of their kiln lives. This is a strategy, a midterm strategy that is only beginning to be exploited. And eventually, primary steel could all be run through DRI and electric arc furnaces globally, with iron being reduced and traded globally. So we'd have a whole new set of trading and supply chains globally in order to make clean steel. The big efficiency jump will be eventually when there's lots of clean electricity and power capacity and recyclable steel. Molten oxide furnaces can take over to supplement electricity. Direct electrolysis, which is being pioneered by Boston Metals, out of MIT, could take over to supplement recycling, which should eventually dominate near the end of the century. So we're talking a whole different way of looking at energy efficiency here. Now, what I'll finally say, those are the three big ones are steel, cement, and chemicals. But the biggest is actually light manufacturing. And the biggest opportunities there are electrification through industrial heat pumps. Now, in some parts of the world, methane is really expensive. Electricity isn't so bad. The jump to heat pumps isn't going to be so far. However, in North America, we face the problem that our methane is incredibly cheap and our electricity is relatively expensive, which puts a huge spark spread gap getting to heat pumps. But I'll stop there, and I'm happy to entertain questions after the other presenters. Thank you very much.
Thanks so much, Chris. I'm going to next turn to our guest from representing Japan. Japan has been one of the leaders in industrial energy efficiency and industrial policy for as long as I know. I've gone back and we've used them as a model for many decades. Yuzo Yamaguchi is Chief Representative of Washington, D.C. office for the New Energy and Industrial Technology Organization, or NIDO, and a special advisor to the Ministry of Economic and Trade, or MITI, for the government of Japan. He joined MITI in 2002 and served as industrial policy, energy policy, and trade policy in various positions within MITI, such as the Ministerial Secretary, Agency for Natural Resources and Energy. He holds a Master's of Science in International Policy from Stanford and a BS in Agricultural Engineering from Kyoto University. And to hear about why Japan is the leading industrial efficiency country, Yuzo.
Okay. Good morning, everyone. First of all, thank you for having me and for giving me opportunity to introduce Japan's energy efficiency policy. I'm Yuzo Yamaguchi, Chief Representative for NED Washington, D.C. office, and a special advisor to Ministry of Economy, Trade and Industry, Government of Japan. I've worked for METI in energy policy for 20 years, and now I was dispatched by METI to work here in D.C. to engage in energy issues. Next page, please. Today, I would like to explain the past trend of the Japan's energy efficiency, policy measures for energy efficiency, Japan's challenges for carbon neutrality, and further policy action for energy efficiency. Next page, please. Japan has engaged in the improvement of our energy efficiency. As this trend chart shows, Japan's GDP has grown 2.5 times from 1973 to 2018, but the final energy consumption has increased by only 1.2 times. This is realized by energy efficiency improvement, especially in industry sector. Next page, please. After the oil shock in the 1970s, energy efficiency has constantly improved, and Japan's energy intensity is the lowest level all over the world. Next page, please. The next page, please. What policy measure realized this energy efficiency improvements? Based on the rational use of an Energy Act, we have had two main measures. One is a business operators report to government, and the top runner program over industry sector, consumer sector, and the transportation sector. Next page, please. The first, what does the business operators report to government with energy efficiency activities entail? Business operators submit periodic reports like 1% reduction effort each year, which METI evaluates. If the efforts are inefficient, METI directs to submit a streamlining plan, and if necessary, METI public the order. This is a strong measure to push a Japanese company who don't feel pressured by publishment. The next page, please. Second, the top runner program is to engage a competition among the company by setting the higher efficiency targets to be achieved in 3 to 10 years. We can set the higher and more practical targets based on the performance of the top runner. Japan has achieved a 49% energy efficiency improvement in gasoline passenger vehicle, 43% energy efficiency improvement in electricity refrigerators. Next page, please. Next page. As you may know, Japan announced a carbon neutrality by 2050. The target was bound by the law that passed in Congress. It is a very rigid target and very difficult to change. Also, in the midterm target, Japan announced a 45% greenhouse gas emission reduction by 2030 with continued efforts toward 50% reduction. Next page, please. Based on this ambitious climate target, we set a new energy strategic plan. What is the role of the energy efficiency in this energy plan? The final energy consumption figure in the slide shows that energy saving is a critical factor. We aim to achieve 26 million kiloliter energy saving. This energy saving means a further 40% reduction, further 40% efficiency improvement from 2013 to 2030. In addition to significant reduction from the 1970s. This ambitious energy saving improvement is faster than the improvement after the oil shock. Next page, please. In order to attain the 2050 carbon neutral target, for the demand side, it is necessary to promote both improvement of energy efficiency as well as the strength of the measures to introduce a non-fossil energy. Next page, please. The number 26 million kiloliter is accumulated by estimation of the energy consumption in the industry sector, business sector, residential sector, and the transportation sector. Promotion of the energy saving building and houses, diffusion of the next car generation automobile, and the measures in fleet transport account for the expected big reduction. In addition to current energy conservation measures, we will both strengthen the rational use of energy acts and as well as support the development of advanced energy saving technologies. Next page, please. Next page. Last month, Japanese government submitted the bill to promote further energy conservation and non-fossilization. We'll make all types of energy, including non-fossil energy, and we will establish a system for the government to require business operators to develop a midterm and long-term plans for conversion to non-fossil and then to report them to the government. Next page, please. Lastly, I would like to introduce the R&D efforts for energy saving in Japan. NEDO, the government funding agency, supports conducting R&D and developing a technology for utilization of unused thermal energy, such as reduce, reuse, and recyclable heat. The budget of these projects is $17 million. Next page, please. The one example is a high efficiency gas turbine. Unstable renewable energy output will be supported by gas turbine output. Under our program, the combined cycle power plant improves the power generation efficiency from 51.1% to 54.4%. Next page, please. The second example is a high performance thermal storage system. We are developing a compact thermal storage system that can utilize the waste heat below 100 degrees Celsius. As this picture shows, the utilization of waste heat can reduce energy by 22.7% and reduce CO2 emission by 30 tons per year. Next slide, please. The third example is a carbon fiber reinforced plastic, or CFRP recycling system. We are developing a technology that regenerates the carbon fiber from a CFRP, resulting in the energy saving. For example, we can achieve a 50% reduction in kerosene consumption in carbonization furnaces. Next page, please. The fourth example is high efficiency power converters. High efficiency power converter system using silicon devices can reduce power consumption by about 33%. These are some examples around the program for energy saving in Japan. We will achieve these ambitious energy saving targets through both strengthening our regulation as well as developing energy conservation technologies. That's all my presentation. Thank you for your kind attention. Thank you very much.
Thank you so much, Yuzo. So let us turn now to one of the technologies that both of our speakers talked about on moving to electrification, which is industrial heat pumps. And we're very pleased to have Jared Leake, who is the Chief Executive Officer with the Australian Alliance for Energy Productivity, with us. Australia has been in the lead on the industrial heat pumps for quite some time now. And Jared brings a wealth of experience where he was with Alfa Laval as Managing Director for Cluster and Cluster President for Oceania and Southeast Asian operations, which is one of the global engineering firms based out of Sweden, and has significant experience in implementing innovative technology and sustainability solutions. So, Jared, please.
Hey, thanks.
And one last thing, Jared gets the award. It is currently 2:28 a.m. in Australia. So thank you so much for really being the heavy lift for us today. So thank you.
No worries, Neil. We've got a good story to share, so I thought it'd be worthwhile. So we just go to the next slide, and I'll go through these slides fairly quickly. So A2EP is where more commonly known in Australia. We're a non-for-profit organisation funded largely by members. And we've been around for about 10 years and really pushing energy productivity. And the next slide, just to talk just a 1 minute about energy productivity, we find that when we talk about more dollars and more value and from less gigajoules, that connects much more with businesses and manufacturers here in Australia. And so we focus much more on production and yield and the value of the goods that are produced. And when framing it like that, much more likely we see to get business cases over the line. So if we go to the next slide, so talk about industrial heat pumps now, and you may say they've been around for many years. Their concept is not new, and a lot of people have them in their own homes as an air conditioner, so that they're really quite well known. But what's new about in using them in the industrial sense? And so what is new is these decarbonisation commitments, certainly being led by the likes in Europe and multinationals there, and with that, things like carbon border adjustment mechanisms are having an impact there and a driver. The second major driver, and this is a little bit unique to Australia for the moment, is we've had a very big rollout of solar PV and wind coming in behind that, and that has changed the ratio for that spark to gas ratio there, making electricity become much cheaper. And so that's heading down to $15. I've left that at Australian, so let's call that $12 per megawatt hour by 2050. 2050. The third major change, which is helping driving industrial heat pumps, is connectivity and cheaper connectivity, allowing end users to be able to better map their heat flows and heat demands, and therefore optimize the installation of a heat pump. So if we go to the next slide there, and I say, you know, what's so fancy, what's so good about them? And it's those three letters of coefficient of performance. And if we compare that to a traditional steam boiler, which is used very much largely across industry, especially in food and beverage manufacturing, most people may think that their boiler, looking at that alone, is around 80 to 87% efficient if they're very efficient. However, if you look at an entire steam system and you consider all the losses along the way, that can be as low as 30% efficient. I think I've been kind here in my calculations to say it's usually about 70% efficient, but most is below that when you look at entire steam system. So if you take the typical industrial boiler producing hot water at say 75, 80 degrees, oops, sorry, I haven't got the Fahrenheit at the top of my mind there, but then you'd look at a coefficient of performance of at least 3, and they can certainly perform up to 6 or 7, no problems there. But that even at a coefficient of performance of 3, you're looking at some 400% improvement there, and that's what does overcome that electricity to gas price ratio. That's what the first thing that does it. It's not the only thing, and we'll get to that in a moment. If we go to the next slide, very quickly, just for later reference, the type of heat pumps that we've been looking at is the mechanical vapor compression, or just standard compression heat pumps using a refrigerant in a closed cycle. And the other one is mechanical vapor recompression, where is an open cycle. And that's very commonly used in evaporation plants and very applicable for distillation columns as well. And if we take the next slide, in terms of applications there, this is provided this from my friend there in Switzerland, Dr. Corden Apagos, and this summarizes some of the applications where heating demands for different services. Certainly anything that's being done in that light blue or even dark blue section is very, very feasible for an industrial heat pump today. Getting up between 100 to 150 degrees is the new boundary, and technologies is coming up for that when you're using these compression heat pumps. For mechanical vapor recompression heat pump methods, then up to 250 degrees is actually quite feasible today. So if we go to the next slide there and have a look at this from an Australian perspective, what is possible in terms of decarbonisation. The chart on the right is really just a breakdown of energy consumption in Australia, and you see 42% is from industry. Of that 42%, 51% or so is for process heating. Of that, most of that, a big chunk of that, is above 800 degrees for things like alumina calcining and metals and what have you. And so that is definitely out of range for heat pumps, and Australia is pursuing a hydrogen future mainly for that very high temperature requirements. But in this chart, really anything below 250 degrees, so making up nearly 50% of that process heating demand, is certainly possible to do with industrial heat pumps. If you look at Australia's overall emissions, a very high emitter, but quite a energy intensive manufacturing country, approximately 20% of Australia's emissions comes from stationary combustion, which is for boilers, burners, and gas turbine running compressors. And of that, around 10 to 15% can be electrified using MVR and heat pump technology. And so in terms of a total, maybe that's 3 or 4% of total emissions. But if you look at what's considered hard to abate emissions from that stationary combustion, it's quite a big chunk of that. So if we go to the next slide, Just some lessons of how this is being supported in Australia. Ideally, I guess you just have a very simple carbon tax or emissions trading scheme, but that's very unpalatable, as you would know in the US, for countries which produce a lot of fossil fuels at the moment. Very hard to get through in a democracy. So then once you start looking at other incentives to make change happen, these are a few things that have worked well in Australia. So in terms of making the ROI better, certain states have implemented energy savings or carbon saving schemes where there's a payment per tonne of carbon. And then that's roughly sitting right now in one particular state at around about $50 per tonne. And we think that's at least at a good level. Somewhere between 50 to $70 a tonne seems to have quite a big impact. Apart from that, there's been some good government programs helping with creating awareness and learning opportunities, and also studies that help remove barriers, and then helping first movers adopt the technology. So in each individual sort of industry or sector, government has been awarding grants to help those sectors and those first movers to adopt the technology, and that's had a reasonable impact. Finally, there's been a fair bit of effort as well in terms of knowledge sharing and sharing what the lessons learned. So if we go to the next slide, let me describe a little bit of the program that A2EP has been working on. And that was a 2 million, call it 1.5 million US funded program from the federal government via the Australian Renewable Energy Agency. And that was completed over the last 3 years or so, which saw the funding of 20 feasibility studies and 20 pre-fees and 7 feasibility studies, largely in the food and beverage area, but also a couple of industrial studies done as well. And this was really to focus on that temperature demand below, say, 100 degrees Celsius. And so this was used to assess the feasibility of different methods. And heat pumps was actually just one of those methods looked at in the pre-feasibility. We also looked at solar thermal, biogas and geothermal, but certainly below 100 degrees, we saw the best potential there coming out of the studies in heat pumps. And then on the next slide, I'll just give you start giving you a bit of a summary of those key lessons learned there. And mentioned before, we talked about the that electricity to gas price ratio is largely overcome by the coefficient of performance, but it's not enough. From the studies and the work that we've done, the most important factor really is this capacity factor. As a heat pump has a cost which is some 8 to 10 times that of a traditional steam boiler on a per kilowatt basis, then you really need to get the most out of that asset. And so the best measurement there is that capacity factor. So how often is that piece of equipment running at full capacity? And you'll see there's, from our studies, a very close correlation to return on investment when you look at a payback for those that had a high capacity factor. In this case, we had some with a higher than 100% because heat recovery was implemented at the same time. So effectively, the overall project ended up with a capacity factor above 100%. But yes, that's because of the heat recovery done at the same time. If you go to the next slide, when we look at the second major lesson learned, and this is very much it helps with the coefficient of performance that is achieved, is that's taking an integrated approach. Not just a like-for-like replacement, not just taking a 2 megawatt boiler and replacing with a 2 megawatt heat pump. It's very much about getting that right. And this is a process that can be used by collecting information, identifying the opportunities and doing some modeling there. And that's a process that can be used to optimize that integrative design. And this includes things like using pinch analysis or an energy and mass balance as well. And then on the next slide, we can say then that the sort of bit of a conclusion for lessons learned is it's very much right sizing that heat pump. Don't look for that straight change in, change out. And you should expect that the thermal capacity of the industrial heat pump is some 50% of the original steam boiler it's replacing. By the time you look at the improvement of reduction of heat loss to the surrounds and what have you, and you size in a thermal battery to remove those peak loads that the steam boiler was sized for, then you should be aiming to be at least 50%. And we've saw some cases down at 40% of what was originally there with a steam boiler of that nameplate capacity. That's when you start seeing some real change in the economics, and all of a sudden it starts the standalone economics makes it viable to go forward. So I'll just finish off with a couple of slides here about some other activities that we did. We did a fair bit of knowledge sharing over lots of different webinars, and these are actually available on YouTube. So if you were to Google A2EP in YouTube or search for that, sorry, you'll see a lot of different webinars that we've done, lots of lessons learned, lots of posts, lots of different things to get the message out there. And there's a publication, I think, in the background for me now, showing that one, and lots of podcasts. So plenty done there. On the next slide, you'll see we also developed a website. If you go to futureheat.info, it's one site where we've taken lots of different resources from around the world and lots of lessons learned. And certainly our latest publication is on there as well. And if you go to the next slide, you'll see this is the tool. We also developed a quick sizing tool so that you can do a little bit of modeling where you may look at the different temperature demands and see how that impacts the coefficient of performance and the costs. And that would certainly help with designers and developers to look at this technology. And then, the final, I think they must be getting close to the end there. And this is the new publication, which summarizes those lessons learned. That's the one right there. And you can download that on futureheat.info. And there's a few other older publications on the next slide where we look at more generic, what they are and the basics there as well. And I think that would pretty much bring me to the end of the presentation there, Neil.
Wonderful. Thank you, Jared. And just a shout out to the A2EP folks on the heat pumps. We relied heavily on their work in our recent industrial heat pump report that came out. Actually, we're doing a webinar this afternoon or later this morning in the case of Jared on that topic. So thanks everybody, and thanks to all of our speakers. I think we've got some really exciting ideas here out on the table. Just a reminder, if you have questions, please put them in the chat and I will try to pose them to as many as I can to our speakers. I want to start with maybe a question to everybody. There were a lot of people who were very impressed with Yuzo's discussion of Japan and what they are committing to and what they've been able to achieve in the past. How do we see that being replicated in other countries around the world? I think, Jared, I know you've done some work there in regions, so sort of that perspective, and then also from a national perspective, Chris, across a transnational perspective.
Yeah. Energy efficiency in Australia is very much driven on the residential side of things with building improvements, and we're certainly seeing the changes to the building codes have an impact there. Industrial energy efficiency, it's usually coming down to state-based programs which are encouraging such reduction and seeing the implementation of such technologies. In terms of a target there, that there's nothing really officially set here in Australia that drives that sort of investment or that sort of change and that sort of government dollars so much, but it's really the federal government is somewhat leaving it to the states and the individual companies themselves who are driving this. So the mantra in Australia is technology, not taxes, and so that support for technology is what's driving that change here.
Chris, any thoughts?
To be honest, I greatly enjoyed the presentations from the two presenters after me, and Jared's is probably the best presentation I've seen on industrial heat pumps globally. So those are amazing resources there. It just struck me as I was listening to him a lot of this is about process integration and upfront CapEx and handling that. One of the things we've been fighting for in Canada is to get an investment tax credit in for industrial heat pumps. It's not there yet, but it's thinking about this systematically. And we have the same gas electric spread that the really wide spread that the Australians have. So it's a question of knowledge, knowing that it's possible to use these instead of boilers, and then handling. It's a different way of thinking about industrial heat and knowing exactly what your heat load, what your end use heat load is, then going to, okay, with a thermal battery and a heat pump, what have you. But then it's about upfront CapEx more than anything else. So those are the comments I have right now. Thanks.
Yuzo, any thoughts on how you can take the Japanese experience and take it global?
Yes, yeah, thank you for the comment. And so now the METI has a lot of policy discussion platform with many governments, including US government. So for example, the last April, former Prime Minister Suga visited the US and had a meeting with President Biden, and we established a climate partnership. And currently, we are discussing with DOE to talk about clean energy promotion and some other climate change the measures that include energy saving, energy efficiency measures. So we are very happy to share our experience and promote collaboration with the US government. And we also have same kind of the platform with the European Union and the China and East Asian countries. So yeah, if it will be contributing the country's energy saving, we are happy to share and share our experience. Thank you.
So one of the themes that we hear throughout all of these, and several people have raised some questions around, is this importance of industrial process heating to decarbonizing the industrial sector. And a couple of questions have come in on sort of what is the role of waste heat recovery in that process. And is it a technology question? Is it a systems integration question on recovering that waste heat? Or is it just simply an energy efficiency solution?
If I may say, Neil, I think it's an integration question. And 20 years as a chemical engineer and visiting a lot of process plant, there's utilities are seen as operating in silos, and of course they're there to support the process plant. That makes sense. But each utility is seen to operate on its own, and I think that sort of mentality needs to change. A heat pump works very well when coupled with the waste heat from, say, a refrigeration plant. Mm-hmm. Or maybe a compressor, an air compressor taking some waste heat from that. That makes a big difference to the performance. And also looking at heat recovery even from waste streams. Often you'll have a hot stream coming from a cooker or some sort of waste stream from a separation process step. And that may have some hot water at, call it 100 degrees Fahrenheit, just going straight to drain, or even being cooled before a drain. These sources of heat need to be tapped into, and that requires much more integration with the utility, from the utilities to the process plant and within the utilities themselves. And it's really quite a different way of thinking about designing that process plant from what we see.
Neil, do you mind if I add to that?
Absolutely, Chris.
Yeah, what we see a lot of in Europe, they've had industrial clusters to allow some of this to happen, Kalundborg in Denmark and a few others. And they're very much going forward with that for sharing CCS collection equipment and transport, potentially hydrogen production and storage. But what hasn't quite translated into the industrial cluster concept is it's also ideal for maintaining proximity of heat sources. So high quality heat comes as waste out of one. It could be dumped into a shared heating system, and you could have a light industrial cluster that collects that and uses that with industrial heat pumps, essentially allowing that heat cascading to occur. And it's once you say it, people's you see the lights go on in people's eyes, but it's very much it's a policy issue, it's a infrastructure issue, it's a land use allocation issue, and it's a matter of thinking about building this into your industrial cluster concept going forward.
Any thoughts from you, Yuzo, on waste heat?
Yes, so let me add a comment. And in Japan, NEDO conducting one project of utilization of the heat waste. So now the problem is heat storage and transportation of the heat. So now the Japanese government and NEDO is making a project in which the automobile companies and the electricity companies and the manufacturing company joined, and to make a consortium to have a demonstration project for the storage of the heat, and trailer that carries the heat to other places. So now the Japanese government provide funding for the consortium and demonstrates the efficiency of the heat storage and the transportation of the waste heat. So that kind of through that kind of measures, we try to push the industry to promote use of the waste of the heat.
So posing another question to you, we talk a lot about technology. All of our speakers have talked about technology. What's the balance between R&D and D, the new technologies versus the implementation of technology that is currently available? And how should we, in a policy context, how should we prioritize those two things?
Good. Charlie, Chris, did you?
Yeah, sure. To be honest, I'm becoming more and more of the mind that we have most of the technology we need at, somewhere between pilot and commercial, and more leaning towards commercial, near commercial and commercial. The question, a lot of this is CapEx. It's getting over the CapEx barrier, the risk associated with that, knowing the demand's going to be there. Like, we know industrial heat pumps, like there have been several very advanced industrial heat pump companies that have gotten up to 150 C and have just gone broke because of lack of demand. We need to create the environment. We need to create the policy environment that allows them to get over that sort of TRL 789 level and into the market consistently, and builds economies of scale such that they can, the components are being built in such numbers that efficiencies of scale start kicking in. So to my mind, our emphasis really should be on, pulling the technologies that we do know work, but are slightly more expensive or CapEx heavy, and getting them into market. And that's going to involve targeted dynamic subsidies. That's going to include, it comes down to infrastructure, what have you. So that I would lead more to that end, but others may differ.
Yuzo, thoughts on that question?
Yes, so it is very important to deploy the current good technologies, and we have some incentive or tax credit or subsidies. But when we think about carbon neutral 2050, that is a very ambitious target. We cannot see the path based on the current technology. So we need a disruptive innovation. So Japanese government provide $20 billion of a green innovation fund to promote innovation. So it is very hard to say that pick up the one, but we need to pursue the both and the deployment of the current technologies and pursue the innovation to attain the ambitious target.
Jared, quick thoughts?
Yeah, I tend to agree that the basic technology is there, but the implementation across different applications is not well done. There's still quite a few gaps actually, especially if you want to start looking at natural refrigerants, CO2, ammonia, propane. There's still a lot of gaps in how they can perform, and still a fair bit of R&D to bring that forward. But certainly the base technology and the building blocks are definitely there.
And I guess finish up briefly with your thoughts on sort of the balance on a policy side between establishing mandates on industry versus looking at providing incentives to industry, whether in the form of tax credits or risk sharing or investment, equity investment. So Jared, do you want to start?
Yeah, just very quickly, I'd say that let's go for incentives. Mandates just seem to be there for businesses to try and find a way around it. So definitely on the much more on the carrot than the stick would be my suggestion.
Yuzo?
Yes, in Japan, we don't like mandatory measures, so we promote voluntary measures. So we have a lot of incentive to promote industry's activities. And but as I said in the presentation, the Top Runner program is kind of the promote industrial activities. So we set the target that other company have already attained, and that target can promote other companies' activities. So we don't want strong monetary measures, but we need to see the very slight balance between the strong measure and the target of the targets. So we often have a close contact with the industry, how to set the target and how to make a measure. So we have a lot of discussion with the industry.
Chris, last final thoughts for the panel?
I guess what I would try to offer is some optimism here. Like, energy, we've been sort of struggling uphill with climate policy for about 20, 30 years here now, but the old window is broken, and policy is getting very, very serious about this, and the willingness to spend some money, the willingness to get in there and figure out the problems is here now. So engage with the policy process, get in there, offer real gritty solutions that, you've got, there's value to be offered here. Get in there and offer it, and things that we've been talking about for a generation are turning into law and policy, turning over very rapidly in several jurisdictions that I know of. So that's it.
Fantastic. Well, to all of our panelists, thank you so much. Apologies for not getting to all of the questions that were posed out there. I see some have been responded to in the chat. And thanks to everybody for that. And thanks for all of your participation. Did want to remind folks that the presentations will be available on the symposium landing page. And then we will also be posting the video of the entire symposium in a couple of days on ACEEE's YouTube channel with links from our website. And with that, my thanks, and I'll turn it over to our Executive Director, Steve Nadell.
Okay, thank you, Neil. And it looks like we have 53 seconds before we're all going to join together but I just wanted to thank everyone for participating, and please give us any feedback you have on the scorecard. I think we'll be sending out a survey about the symposium. Tell us how we can do better. But all the, as Neil noted, the recordings will be up soon. All the presentations are either up or will be soon. So I hope you got a lot out of this. There we. Oops, nope. Okay. So thank you very much.